An immense cosmic boulder rockets in from deep space on a direct collision course with Earth. When it hits, it unleashes a global catastrophe. This is not science fiction. It happened 65 million years ago. And much of life on Earth, including the dinosaurs, died. Today, many scientists believe that this is not a one-time event, that what wiped out the dinosaurs could happen again. And we could be next.
Will another impact occur? You bet. It's going to happen again. The Earth is sitting out there with a bullseye on it.
What are these mysterious invaders? Where do they come from? And if one threatens the Earth again, will we be able to stop it in time? We think of comets as some of the heaven's more spectacular pieces of eye candy, and most are benign, orbiting harmlessly around the sun. But some will inevitably collide with another body, like Earth. At speeds of 25,000 miles an hour, even a small cosmic raider can wreak enormous havoc, as one did in Arizona's northern desert 50,000 years ago. It began as a brilliant glow in the northern sky. It was over in an instant. The huge rock, about 65 feet wide, left a crater almost a mile across and 750 feet deep. In cosmic terms, this was a relatively small collision. If the same boulder struck today, just 35 miles west, it would destroy the town of Flagstaff, Arizona, and its population of 56,000 people. An even larger collision with an object a mile or more in diameter could cause devastation on a global scale.
An impact by a comet will kill so many people and can produce such long-term changes in the environment that it can be a complete catastrophe for all of humanity.
Scientists now believe a single blast from space helped wipe out the dinosaurs 65 million years ago. A comet or asteroid about 6 miles across slammed into Mexico's Yucatan Peninsula. It dug a crater nearly 50 miles wide and 20 miles deep in less than a second, and unleashed an explosion more powerful than all the world's nuclear weapons combined. The force of the shockwaves triggered earthquakes worldwide and sent tsunamis surging across the oceans. A mammoth dirt cloud erupted miles into the sky, engulfing the globe and blocking out the sun for years. The dinosaurs slowly perished, and they were not alone. More than half of the Earth's species were also wiped out. In our solar system, there are two kinds of cosmic bullets capable of devastation on a planetary scale: asteroids and comets. Asteroids are essentially tiny planets, dense boulders of rock and metal left over from the formation of our solar system 4.6 billion years ago. Most are bunched between Mars and Jupiter in an orbit called the asteroid belt. Comets, on the other hand, are far more mysterious. Though also formed at the birth of our solar system, they are made up of rock and ice. Many, like Comet Halley, orbit the sun in predictable paths on predictable schedules. But there are countless others we know nothing about. They come hurtling out of the ether at unimaginable speeds, of up to 100,000 miles per hour. For scientists peering into space, they appear as lumps of charcoal on a black canvas, invisible until they are practically upon us. Only near the sun do comets become easier to detect. These icy bodies shed gas and dust as the sun warms them. When light hits the debris, they blaze into view and can be seen for millions of miles. But by that time, if one is headed for us, it may be too late to do anything to stop it. To date, more than 1,000 comets have been identified. Every year we spot perhaps 100 comets we've never seen before, entering the inner solar system. Each new arrival increases the odds that one will eventually strike the Earth.
The Earth is in a cosmic shooting gallery. We get hit by pieces of comets and asteroids of all size, and the big ones certainly pose a very real threat.
It's only a matter of time before the comet is in the same place as the Earth.
Giant pockmarks all over our planet testify to past assaults. And these collisions may be more frequent than we like to think. The latest happened a little more than a century ago. In 1908, a massive explosion rocked Tunguska in Russia's remote region of Siberia. Eyewitnesses described a flying star with a fiery tail. The sky opened to the ground, and a fire brighter than the sun poured out. Whether an asteroid or a comet, it collided with the Earth's dense atmosphere at such a high rate of speed, the friction caused it to explode in midair.
It blew up 5 miles above the surface of the Earth, creating this huge explosion and lit up the atmosphere for days. You could actually read in Europe at night.
The Tunguska blast, as we now call it, was bigger and more powerful than the eruption of Mount St. Helens. It left no telltale crater, but it did flatten a forest of millions of trees over hundreds of square miles, an area bigger than that of Washington, D.C.
If that would have happened over a metropolitan area, it would have just wiped out the population for thousands of square kilometers around the impact site.
To astronomers, Tunguska was a near miss, a relatively minor impact. A major impact from a comet would have devastating effects. Imagine the following scenario. Scientists have spotted a 2-mile-wide comet on a collision course with Earth. It's too late to stop it.
The first thing you'll know is when the sky lights up and the ground shakes.
Brilliant meteors streak across the sky as the giant comet's debris strikes the Earth's atmosphere. Forests catch fire, ignited by the superheated air. When the comet hits, the blast kicks up millions of tons of fiery rock and dirt. The airborne debris blankets the planet and blocks out the sun. Day turns to permanent night, bringing freezing temperatures and year-round winter. It takes more than a year for the dust to settle and sunlight to filter through the clouds. When it does, the Earth starts to warm quickly. Elevated levels of gases created by the fires turn the planet into a sweltering greenhouse. Millions of species of living things that survived the earlier cold cannot take the heat. They die. It takes thousands of years for life on Earth to recover. How great are the odds a comet will strike the Earth?
Will another impact occur? You bet. It's going to happen again. The Earth is sitting out there with a bullseye on it.
The chances of a major impact in our lifetimes may be slim, perhaps on the order of 1 in 100,000. But astronomers the world over are working fervently to understand these strangers in our midst, struggling to learn what comets are and where they come from. Mankind's ultimate survival may depend on our ability to stop one before it strikes. Scientists have been gaining a deeper understanding of comets and the level of threat they pose to planet Earth. We've long known they were out there. Even the ancients noted their periodic visits. In the 17th century, stargazers observed how some comets orbit the sun in regular intervals, like the planets. One astronomer even predicted the return of the comet that now bears his name, Halley. But no one knew what they were made of or where they came from. As late as 1950, astronomers could only guess at their true nature. Fred Whipple, the father of cometary astronomy, envisioned comets as flying mountains of frozen gases, ice, dust, and dirt. He called them dirty snowballs. He theorized that as comets neared the sun, they shed dust and gas as their ice vaporized, forming their signature tails. It wasn't until the 1980s that astronomers were able to test Whipple's theories by approaching these speeding ice balls. What they discovered surprised them. In 1985, as part of the International Sun-Earth Explorer program, they flew a spacecraft loaded with sensors through a comet's tail. In 1986, the European Space Agency sent a craft called Giotto to study Comet Halley's nucleus. The scientists feared the debris flying from Halley would destroy Giotto. It didn't. The craft not only withstood the pummeling, it sent back amazing photos of a cratered sponge-like surface with jets of gas shooting from within. Suddenly, scientists began to wonder exactly how rock-solid comets really are. In the year 2000, they got more clues. On its approach to the sun, a comet named Linear unexpectedly blew apart. Earth and space-based telescopes captured the explosion, allowing scientists to analyze the chemical composition of the nucleus for the first time. That information, combined with data from the earlier flybys, confirmed what astronomers were beginning to suspect. Comets are not ice-hard. They are surprisingly fluffy, porous, and fragile. Johns Hopkins University's Hal Weaver simulates the comet's unexpected makeup.
Okay, we're going to make one of the most primitive objects in the solar system, a cometary nucleus. These cotton balls are just barely held together. One of them just fell off. And as comets pass through the inner solar system, they get heated up. And sometimes these little cotton balls just fly off and break apart.
Comets consist primarily of chunks of water, dirt, ammonia, and carbon, molasses in this experiment. They are permeated throughout with frozen gas, what we know as dry ice. As comets near the sun, the ice vaporizes, releasing gas and dust that form the characteristic tail.
You see the ice subliming, going directly from the solid phase to the vapor phase. This is exactly what happens when a comet is going around the sun. It doesn't look like your original concept of a comet, does it? But it's a single solid object. You can see active regions on the surface bubbling up. We get activity only on specific spots for a lot of the comets. And as they fly by through the inner solar system and heat up, sometimes chunks just drop off. And sometimes we see the comet completely disintegrate.
This new knowledge about the fragility of comets may seem reassuring. How can they do much damage? But as they race through space at more than 7 miles a second, even small comets can spell disaster. Donald Yeomans studies comets for NASA's Jet Propulsion Laboratory.
Well, they are fragile, and you could break them apart with your hands perhaps, but they're huge. You know, they're 10 miles in diameter, and so it doesn't really matter that they're fragile. They're so big that they've got a lot of mass, and it's mass and velocity that's important when they hit.
We can't stop a comet heading toward Earth if we can't see it. But that's another mystery plaguing scientists. Where do these cosmic travelers come from? Astronomers have long observed comets emerging from deep space. To know exactly where they've been, they would need to get their hands on actual comet dust, a record of a comet's birth and its travels.
3, green board all the way across. 2, we have main engine start. 0, and liftoff of the Stardust spacecraft.
In February 1999, NASA's Stardust spacecraft began a voyage to rendezvous with a distant comet named Wild 2. Its bold mission was to collect dust from Wild 2 and return it to Earth. Nearly 4 years and 2 billion miles later, it finally caught up with its quarry. By raising a giant gel-filled petri dish, roughly 1 foot in diameter, it collected more than 1,000 samples as it sped by the comet at over 13,000 miles an hour. The mission was a remarkable success. In January 2006, 7 years after liftoff, Stardust's cargo capsule returned to Earth. The contents have been a treasure trove for scientists. They will spend years analyzing the dust, but already they've learned something surprising about these mysterious space travelers. Comets have origins similar to our Earth.
We thought comets all formed from stuff pretty far from the sun. We're finding in this comet grains that formed right next to our sun.
Born near Earth when our solar system was formed, the comet then fell into an orbit that took it far beyond. According to surprising new data from Stardust, much farther than scientists once thought.
There's not just material from our own solar system at its birth stages, but also materials from different distant stars mixed in as well. And also materials forming far from it and just sort of like passing by. It's a real grab bag of things in our galaxy.
Preserved since their birth by the deep freeze of space, comets are a record of our solar system's beginnings. Now armed with their new research into the mystery of comets, scientists can theorize about where comets come from and how they were born. The story of the comet's origins begins 4.6 billion years ago. Our solar system is in the midst of a fitful birth. In the center, a cloud of gas and dust begins to contract into an immense disk. The disk's powerful gravity sucks masses of matter inward. Pressures and temperatures soar until the enormous dense ball ignites, its gases and matter imploding in nuclear fusion. A star, our sun, is born. Left to orbit the newborn sun is a fog of debris. The fragments careen into one another and clump together into celestial dust balls. Over millions of years, these monster clumps grow larger as they orbit the sun, until they form an array of planets including our Earth. But some dust balls, future comets, do not merge and condense into planets. A billion or more slowly gravitate to an orbit between Neptune and Pluto, a region called the Kuiper Belt. Trillions of others are exiled partway to the next star, to a nebulous realm called the Oort cloud, hurled outward by the gravitational fields of large planets like Jupiter. They have elliptical orbits that vary greatly.
You've got the Kuiper Belt region of comets, and they're mostly compressed into a plate-like distribution. But in the Oort cloud, which is 1,000 times further out, they're in a veritable cloud. So you've got objects in this kind of an orbit, this kind of an orbit, that kind of an orbit. They're coming in from the outermost edge of the solar system.
Amazingly, astronomers did not confirm the Kuiper Belt's existence until 1992, even though it is part of our solar system. Today, they believe the Kuiper Belt is the outer range of comets with the most stable orbits, those that enter the inner solar system every 300 to 200 years. The best known of these, Halley, returns every 76. But it is the second region, the Oort cloud, 2 light years away, that troubles scientists most. Scientists believe an occasional disruption, like a change in a star's gravitational field, will eject a comet from this cloud. It can then fall under the gravitational pull of our own sun and start a journey toward our inner solar system, taking thousands of years. Scientists have no way to predict when these comets will appear, and they can come from any direction. One may already be on a collision course with Earth. In 1997, the world awakes to a comet secretly entering our solar system. 2 amateur astronomers spot an unknown intruder near Jupiter, more brilliant than any they've seen before. Dubbed Hale-Bopp after its discoverers, it was a visitor from the Oort cloud, on its first journey around the sun in almost 5,000 years. As it warmed and its frozen innards vaporized, Hale-Bopp grew dazzlingly bright. Its thick tail reflected the sun's rays in all directions. The comets we most often see are little more than asteroids. Their gas and loose dust burned off in their frequent jogs around the sun. But comets like Hale-Bopp, just out of the Oort cloud's deep freeze, have plenty of ice and dust to shed.
They've got water ice, they've got carbon dioxide ice, dry ice, they've got carbon monoxide ice, and all of these ices are much more volatile than water. So when they get in the inner solar system, they go nuts.
Fortunately, we could marvel without fear at Hale-Bopp's glorious moment in the sun. It sailed by unobstructed, 122 million miles from Earth, just a bit farther away than our sun. But what if it had been on a collision course with our planet? When detected, Hale-Bopp was less than 2 years' journey from Earth. Perhaps not enough time for us to stop it. If we could track comets in advance and plot their orbits, we'd likely have many years of warning if the orbits veered toward us. It may seem like a tall order to scan the vast sea of space for that one pinprick that could spell disaster. But that's exactly what astronomers are doing. In 1992, the US government launched an aggressive program to analyze the threat comets and asteroids pose to Earth. It's called the SpaceGuard Survey. Today, scientists all over the world are involved in the painstaking process. They point their telescopes at a single region of the sky and take periodic snapshots. Then they line up the images, looking for anything that moves from frame to frame.
We are looking first for the larger asteroids and comets, the ones a mile or so in diameter, and eventually we'll extend it to the smaller ones.
Scientists estimate our solar system has about 1,100 comets and asteroids that are half a mile in diameter. So far, searchers have identified over 700 of them. And those are just the giants that could do apocalyptic damage. We may never be able to locate every threat. There could be millions of comets and asteroids that measure 300 feet or so, the length of a sports field. That's more than 3 times the size of the rock that slammed into Arizona 50,000 years ago. Still, telescopes are our first line of defense against what could be a major disaster for our planet.
If you don't look, you won't know anything's coming. We would be taken by surprise just as much as the dinosaurs. If you do carry out a survey, then you hope that you can have warning. But it's one or the other. Either you have years or decades of warning, or you're taken completely by surprise. There's nothing in between.
There's 3 things that are important. You have to find them early, you have to find them early, and you have to find them early.
Suppose we do detect a comet headed for Earth. Then what can we do? Scientists have just started to come up with solutions. One of the leading ideas, smash a rocket into it to slow it or knock it off course. That's harder than it may seem. If comets were hard ice balls, as first thought, a powerful thump from a rocket might do the trick. But some comets may be porous. They could just absorb whatever we throw at them, like a sponge. In 2005, scientists were ready to test their theories about how a comet would react when it was hit. They were going to try to crash a rocket into one. At the dawn of the 21st century, after puzzling over the mystery of comets for 200 years, astronomers are ready to launch their most ambitious experiment yet. They call it Deep Impact. They're going to see what happens when a spacecraft slams violently into a comet at 23,000 miles an hour. Deep Impact's primary goal is to peer inside a comet. That inner material has remained relatively unchanged since the solar system was formed and could provide clues about the solar system's beginnings. But astronomers also hope to gather ideas about how to stop a comet heading toward us. Deep Impact began here at NASA's Vertical Gun Range in Mountain View, California, where it was the job of Dr. Pete Schultz and his team to figure out what the comet would do when it was hit.
This particular instrument allows us to fire a small sphere, about 1/4 inch, at speeds that are maybe 6 or 7 times the speed of a rifle bullet. This whole assembly rotates up to an elevation where the gun is basically 3 stories high. This allows us to send the projectile through different openings in the chamber so that we can impact a flat surface at different angles.
Scientists believe comets vary in their makeup, so Schultz and his team built several different models, then hit each with shot from their ultra-high-speed gun.
The first scenario is what happens if we impact into something that looks like lunar dust. The second one is what happens if we impact into fluff. And the third one is what happens if we impact into a fluff covered with an organic layer. As we go down and look at the evolution of this crater, we find at the very end, after it's finished, we can still see the crater here. But in these two cases, when we're using fluff, we can't see the crater. It's completely masked.
The fluff completely absorbed the projectile, a frustrating result for scientists hoping to get a look inside. And there was another possibility Schultz had to consider. What if the entire comet is extremely fragile and porous? He searched for a substance for that simulation.
The comet may be sort of like a fluff ball. It may have been very low density. What do we do to try to simulate that? The best thing probably is a complex organic. What would that be? Cotton candy. We've got our comet made of cotton candy. Let's turn off the lights and let's get out of here.
The projectile soars right through the comet,
Can you back her up?
but the force shatters it.
Oh my God! There's no more comet, that's for sure. What a mess.
But this is not good news. A shattered comet can be even more dangerous than an intact one. The pieces tend to remain on the same path, turning one projectile into many. In 2005, once the team completes their tests, NASA is ready to take the plunge. It will try to drive an 820-pound impactor into a comet to find out what's inside. Deep Impact's principal investigator is the University of Maryland's Dr. Michael Ahern.
So here we have the model of both Deep Impact spacecraft. Many people think it was only one spacecraft, but it's really two. The flyby spacecraft has all the instruments on this platform on one side. And if I turn it around, these are the solar panels that provide the electric power. Here's the impactor. That is 1/3 of a ton geologist's hammer with which you hit something to see how it behaves when you hit it.
January 12, 2005. After 6 years of study and preparation, Deep Impact is ready for liftoff.
3, 2, 1. We have ignition and liftoff of a Delta II rocket carrying Deep Impact.
The spacecraft's destination is a 4-mile-wide comet named Tempel 1. Discovered in 1867, it's well known to astronomers. It orbits the sun every 5.5 years and has lost much of its gas and ice.
People would argue that you should preserve the comets for posterity, but doing a violent study on one that is just typical of a whole class seemed to us to be the right choice for science.
Deep Impact takes just 5 months to reach Tempel 1's orbit. On July 2nd, 2005, it turns and points its cameras at the comet, 500,000 miles away. Then it releases its impactor. If all goes well, the collision will blow a hole in Tempel 1 about 600 feet across and 5 stories deep, about the size of the Roman Colosseum. But it might destroy the comet by breaking it apart. Back on Earth, hundreds of scientists hold their breath.
We lost signal, and we had to stand there and wait around. So everybody was trying to be, go keep busy and not feel anxious.
But just in time, the signal returns.
The energy went in, bounced back, and drew out all this material from beneath the surface, which was then exposed out in space into sunlight. And so this is scattered sunlight off of all of this debris that was excavated from the interior of Comet Tempel 1.
The half-mile-wide comet and NASA's 820-pound craft have collided at 23,000 miles an hour. The explosion is equal to nearly 5 tons of TNT. It completely vaporizes the impactor, and it kicks up far more dust than anyone expects.
One of the reasons it was so dusty is that the particles were much smaller than we thought. This is a very fluffy body.
The amount of dust is a telltale clue to the comet's makeup. Tempel 1, at least on the surface, contains far less ice than scientists expected.
There was no way that there were large blocks of ice anywhere or rock. And that really is helping us formulate how did these comets get put together? How did they break up? This is the first data we've ever had. So in that sense, it's revolutionary.
Analysis of the dust showed molecules containing carbon, organic material. So it's plausible that comets could have brought such material to Earth early in its history. A return mission is planned to take another look.
In 2010, NASA will have redirected the Stardust spacecraft to go back to Tempel 1 and look for the crater that we formed to see what happened to the surface and the rest of the comet when we impacted it.
Scientists hope to learn something else from deep impact. Clues about how to stop a comet from colliding with Earth. Some thought deep impact might knock Tempel 1 into a slightly different orbit. But the comet has continued on exactly the same path as before.
It was a secondary objective of the Deep Impact mission to come up with a plan to mitigate an impact if we had to.
Did we figure out what it would take to move a comet out of an orbit that was intersecting the Earth? We didn't figure out enough.
Despite the inconclusive results, many still consider deep impact the best model for stopping a rogue comet. The key will be to send a larger spacecraft and to hit the comet much harder.
Let's assume that this is the cometary nucleus. One way of slowing it down and having it miss the Earth in 20 or 30 years' time is to simply run into it. Bam. If that doesn't work, do it again. If that doesn't work, do it again.
But some think we'll need a more radical approach. One plan calls for detonating a nuclear warhead near a comet to nudge it onto a different path. Controversial proposal because of the unknown consequences of releasing radiation in space. Others have called for drilling into the nucleus and setting off a blast inside. But as we've seen, this has the danger of turning one deadly projectile into many. The pieces could continue on the same orbit, and like the blast from a shotgun, wreak destruction over a wider area. Some have proposed less violent yet equally intriguing solutions. They suggest putting lasers on the moon, where the Earth's atmosphere would not deflect them. The lasers could bore into a comet and melt its icy glue. We might even hitch a spacecraft to a comet and tow it out of our way. Whatever the solution, all ideas remain on the drawing board.
If a comet is on a collision course, we may not be able to do anything.
Even if we could tell tomorrow that something is headed our way, we don't necessarily have the means right now to protect ourselves.
For one day, we might look to the heavens and find the comet with our number on it, headed our way. March 23, 1989. A half-mile wide asteroid is about to cross Earth's orbit. It arrives just 6 hours after the blue planet has passed by. This is the equivalent of two airplanes missing each other by seconds.
Humanity collectively should fear them because they do hit the Earth.
But while comets can be emissaries of death, we're learning that surprisingly, they can also be agents of rebirth. In the turmoil of the early solar system, millions, if not trillions, of comets and asteroids pelted the primordial Earth. The massive collisions turned matter molten, peeled back the planet's crust, and sparked firestorms that engulfed the globe. Today, if not for the continuous erosion of wind, water, and heat, the Earth's surface would look much like the Moon or Mars. But as scientists are now learning, that bombardment also produced unexpected results. Those icy comets may have brought the water that now swells the Earth's oceans. They may also have delivered organic compounds. From that combination of water and organic materials, life slowly evolved. Comets might still be helping support the Earth's living things. Galactic snowballs are regularly drumming Earth's atmosphere, millions of times a year. Some scientists say the ice balls, some as big as houses, disintegrate when they hit the atmosphere. But they leave behind fleeting clouds of water vapor, sustenance for life below. New York University's Dr. Michael Rampino takes the theory one step further. He believes the Earth endures a cosmic assault like the one that helped form it every 30 million years. Each barrage heralds a new cycle of death and new life. It's called the Shiva hypothesis, after the Hindu god of destruction and creation.
So there was a period when there was a real reduction in the forms of life, and that's followed by an explosion of life, because whatever survives can fill in all the environmental niches that were opened up by the extinctions of the organisms that used to fill those niches.
According to the Shiva hypothesis, the cycle will begin again in about 25 million years, when another barrage from above will cause a global catastrophe and mass extinctions. It's a controversial idea. Most scientists don't see solid evidence of periodic, not to mention predictable, bombardments. And no one has been able to explain why such periodic impacts would occur.
Now, there has been suggestions that these impacts are periodic on the order of 30 million years or so. The evidence is weak. I think the jury is still out on the so-called Shiva hypothesis.
One thing is clear. There's much more we need to learn about comets. One experiment that hopes to add new information about their life-giving properties is already underway. A brainchild of the European Space Agency, the Rosetta mission will land a spacecraft on a comet for the first time.
We want to see what is actually in the nucleus and on the nucleus, and the only way you can study that is to put a lander down.
Rosetta left Earth in 2004. In 2014, it will rendezvous with Comet Churyumov-Gerasimenko. As it follows the comet toward the sun, it will send a mini laboratory to its surface. The lander will drill into the nucleus and extract samples. Then it will analyze them.
We didn't bring the sample back to the Earth, to the laboratory. We bring the laboratory to the comet and study it there.
Rosetta will be a big step toward learning whether comets could have jump-started life on Earth billions of years ago. In future missions, astronomers hope to probe even deeper beneath the surface of comets. The goal remains to increase our understanding of their makeup and their origins, as well as to strengthen our knowledge of how to stop one. But the next time a comet blazes across the sky, we can look at it in a whole new light. Not simply as a harbinger of death, but as a potent instrument in the evolution of life.
This is the National Geographic Channel.